like to give a little unorthodox lecture, just so that, how should I say, just for fun. Action potentials I hope you have encountered many times, at least in biophysics. So I just would like to say a few words that I think are important or interesting regarding action potentials. Well, of course, if one wants to give a real scientific lecture, then one must start by saying that the ancient Greeks have already told us. Well, actually, they indeed did. They thought that since our hands and legs are moving, and they came to the idea, which was then forgotten for a couple of hundred years, more than 1,000 for that matter, that somehow our brain has to do something with that. They thought that the brain secreted something, a fluid or a spirit of some sort, that flows through the nerves to the muscles. So actually, although they had no technical clues, which is not quite correct, nowadays research realizes that Greeks had more of a technical civilization that we had originally thought. They came to the idea of something has to move along the nerves. Actually, electricity as is, well, of course, everyone, even back in the ancient days, knew that if they do this, then the hair would go up like that. So, static electricity has been known in Greece and then for many years, but actually that there is electricity that can move, that comes from the work in the 1700s, that is somewhat a little over 2,000 years to 2,500 years after the Greeks have already knew what electricity is, from Galvani, who actually discovered that it's muscle that produces this, and hanging muscles on his balcony make the touching iron and copper bars on the balcony make the muscles contract. And that's how electricity was discovered. So this is how it became known that there is something of an animal electricity, and that it led to the recognition of current, that this electricity can move. Galvani gave the name for certain batteries, and his student or associate, Alessandro Volta, gave the name to what now we measure electricity or potential in, that is in volts. Later on, some 70 or some years later, we are still in Italy, a guy demonstrated that biological systems can generate direct electrical currents. And then a French guy, following on these Italians' work, did a lot of work on nerve impulses and defined the term electrophonus. Something that you have heard probably in your previous lecture. Well, the breakthrough came by studying these little animals here. Can anyone recognize them? Squid. The term squid giant axon probably you have heard, yes? Well, the measurements on these squids and giant axons, you know, the squid is good because of two terms. One is because the axon is very big and you can easily work with, and the second is it is very easy to catch. Do you know how you catch squid? Have anyone? You know, you just have to take a hook, a lot of hooks, throw it in, and make the hooks go around and around, and since it moves, the squids will jump on it, and you just can catch the squid by the hundreds. So people doing that during the Second World War on the southern shores of England, actually two guys. One is called Alan Hodgkin and the other one is Andrew Huxley. Well, actually, they were both in the physiology department of the University of Cambridge. Huxley was a young postdoc. Huxley was a medical student. And it was during this war that Huxley, this guy, went to one of his clinician friends and asked him what would he advise him to do. And the guy said to him, you know, it's war. Everyone who knows something with medicine is taken to the war. So I have a good friend called Hodgkin who is down in Devon working on some strange things, but interesting. So why don't you go down there and join his work? So he went, that is Huxley, and this generated what we call the action potential and all that. Although I didn't have the opportunity to actually talk much with Hodgkin, but Huxley I know very well. Sorry, I used to. He died a little less than a year ago. Yeah. He continued on up to the action potential with muscle, and we owe a lot to what they did. So how do these sodium channels work? This is something I hope everyone knows. Very simple idea that the two guys put together and got their Nobel Prize for that. That you have at the resting membrane potential a channel which is closed. So sodium ions, although they would like, because there's more outside than inside, they cannot go in. When the membrane is depolarized, then this channel changes its conformation, becomes open. We call this process activation, and then sodium ions, due to their electrochemical gradient, move into the cell. If the depolarization is sustained, then this little piece inside changes again its conformation and flunks this, what we call pore, on the channel. So although the channel seems to be open, it is actually not, and we call this state of the channel inactivation and inactivated state. And the system always goes in this direction, that is from a resting membrane potential to activation first and then inactivation. Simply because this change happens faster than this change here. This direction, ladies and gentlemen, does not occur. The channel will not go from this state to this state. In order to get this out from here, you need to move the membrane to its resting potential. So this is the road back. So the channel from closed goes to activated, inactivated. Then due to the repolarization, that is going back to the negative membrane potential, makes the channel to stop being inactivated, but that also closes the channel. This step is always faster than this step, even in this direction. So going from here to here, first we'll close the channel, but it will still remain inactivated, then the inactivation is removed. So in order to get this, you need a substantial and long repolarization. On the other hand, they describe not only sodium channels, but potassium channels, which are much simpler in certain terms. That is, there is more potassium inside than outside, so at rest, the sodium would like to go, well, potassium would like to go out, but it can't because the channel is closed. If you depolarize the cell, the channel opens and potassium ions can go out. In this case, since there is no inactivation, please understand that under physiological conditions, if you really try, you can make potassium channels inactivate, but that never happens under physiological conditions. The reason I'm mentioning it inside because certain pathological cases, mutations, can alter the function of potassium channels. You might have heard of, for example, sportsmen falling dead on the field. Those are due to, in many cases, potassium channel mutations. Okay, so the usual action potential that you have probably all seen. So I just wanted to make sure that everyone is clear on this, that if you take an axon and you start with a resting membrane potential of minus 70 millivolts or so, then you have something that stimulates the cell. This reaches a threshold, and from then on, the action potential goes on its own. Depolarization occurs due to the opening of the sodium channels. That is, at rest, we start with both sodium and potassium channels closed, and then, upon depolarization, these voltage-gated fast sodium channels open. They open much faster than the potassium channels. Please mind that this lasts 1-2 milliseconds. That is 1/1000th or 2/1000th of a second. So when I'm saying fast, I mean really, really, really fast. Then, with the system becoming depolarized, plus 35 millivolts or so under physiological conditions in a mammal, in a human being, then sodium channels become inactivated, whereas potassium channels activate. That is, they open, and this opening of the potassium channels allows potassium ions to go out. Please note that sodium ions coming in makes positive charges appear inside the cell. That helps depolarization. Potassium ions going out on these open channels make potassium ions going out from the cell, which leaves negativity inside, so that is repolarization. Since the sodium channels are inactivated, potassium channels are open, the repolarization goes beyond the resting membrane potential. This is what we call after hyperpolarization. This after hyperpolarization will then bring the system back to where we started from. Both channels, voltage-gated sodium channels and voltage-gated potassium channels, will close. So, please note that repolarization is ensured by the activation of potassium channel and the consequent potassium efflux, and not the sodium-potassium pump. The sodium-potassium pump is not responsible for the repolarization. I am making this statement because many cases I find in exams that students tend to believe that the sodium-potassium pump is the system that generates that brings back the membrane to its rest. This can be simply demonstrated by measuring action potentials if the pump is not working. And thousands of action potentials can be produced, even if the pump is not working. However, please note that the pump is responsible for maintaining the concentration difference on the two sides of the membrane. If you put these two things together, you will see, I hope this has been mentioned in biophysics or previous lectures, but if it has not, I would like to say it very clear that an action potential will not alter the concentration gradient across the cell membrane. The amount of sodium and potassium ions moving in one action potential is negligible compared to the concentration gradient that exists. Thousands of action potentials are needed in order to appreciably change the concentration gradient for sodium or for potassium. If one looks at how much of the channels is open, we measure this in terms of conductance. I hope you have heard the term. If you haven't, please note that you will have to do this in simulations at the lab. You can see that this is the action potential here in dashed lines. In magenta, you can see the conductance of the sodium channels, showing a rapid opening of the channels and then inactivation of the channels. And therefore, at this point, none of the channels are open. In green, you see the conductance of the potassium channels, note the delayed opening, and you reach the maximal conductance during repolarization. And please also note that after the action potential has reached the original value in terms of membrane potential, the potassium conductance is still elevated as compared to at rest. Therefore, the membrane potential keeps on going negative until the potassium conductance reaches the value that it had before stimulation. Activation, of course, as we have discussed, is due to the opening of the sodium channels, and this decline is the inactivation of the sodium channels. This opening of the potassium channels gives rise to the increase in potassium conductance. We can divide the period of the action potential based on the fact that can we evoke a second action potential with a second stimulus after the first. Well, we say that the membrane is in an absolute refractory period when a second stimulus will not initiate a second action potential. This is due to the fact that sodium channels are inactivated in a certain period of time. Therefore, no matter what you do, how you stimulate the cell, a second action potential will not be generated. We say that the membrane is a relative refractory period when a second stimulus can evoke an action potential. However, the second stimulus has to be greater than the original stimulus was. Then we say the membrane is in a relative refractory period. This is due to the fact that some sodium channels are available for repeated activation, but not all. Okay? Absolute refractory period and relative refractory period. If you would allow me to go back, this part of the action potential is an absolute refractory period. This part of the action potential is the relative refractory period. Obviously, when we are back here, the refractory periods are one, and the membrane becomes stimulatable again. Please also note that the fact that there is an increased potassium conductance during this period of time, it contributes to the fact that there is a relative refractory period, even though the membrane is back at the resting membrane potential, or even negative compared to that. Why is it good that we have refractory periods? It is important because it prevents the fusion of action potentials. Therefore, it allows discrete impulses to propagate along the membrane. If you wish, the system, nowadays it's easy because everyone knows computers, so we can sort of use the 1 and 0 coding. Is there an action potential coming, or isn't there an action potential coming? Two action potentials will never fuse. There will always be a time between the two. So we can always say and count, so to say, the number of action potentials arriving during a certain period of time. So these guys, Hodgkin and Huxley, designed and made us understand that this is a very simple self-generating cycle that starts with a depolarization, which then activates the sodium channels, which then initiates a sodium influx into the cell. And since positive charges go into the cell, this initiates depolarization. So we are generating a cycle which goes on and on and on as long as we allow it to do. And how and what stops this cycle? This is a, if you wish, positive feedback. Something that starts it, a depolarization, results in further depolarization. One would assume that this would have to go and never stop. So nature invented two things to stop it. One is that if the depolarization is big enough and sustained, then sodium channels inactivate. That is, there is no further activation of sodium channels. And second, as depolarization goes further and further, the system approaches the equilibrium potential of sodium, plus 55 or so. Did equilibrium potential been described? Very good. So the system approaches the equilibrium potential of sodium. Therefore, the sodium influx gets smaller and smaller because the driving force for sodium gets smaller and smaller. This, of course, explains the fact that the action potential, the peak, the top, can never go beyond the equilibrium potential of sodium. Sodium is driving the depolarization, and it will not go in if the equilibrium potential would have been reached. It is actually never reached because potassium channels open in the meantime and they oppose it. So action potentials never go up to plus 55, only to plus 35 or so, because of the opposing potassium flux in the other way. This also teaches that if you look at the other way, that is, follow this thing after the action potential, this will explain what happens during the repolarization and tells you that the repolarization can never go beyond the equilibrium potential of potassium. So actually, the action potential is always, if you wish, shot between two values, down below the equilibrium potential of potassium, up top, equilibrium potential of sodium. The two are never actually reached, plus 55 and minus 95, but somewhere between is where the action potential goes. So, in order to understand how this really, these absolute and refractory periods and this all or nothing law, which I will come back to in a second, but I suppose you have heard the expression, that is, if the action potential starts, it does everything. I decided to show you a simple model. Please understand that the model is not mine. The model has been designed in England, where the action potential has actually been originated. Actually, the model is quite old. It has been invented before the action potential has actually been known, but has only been applied to the action potential very recently. And the model, ladies and gentlemen, is this. This is the Kohler-Windom elongated toilet. And funny as it might seem, I would like to make you understand that it is a very good model of the action potential. In order for this demonstration to work, I would like to ask the audience to please be silent, because the noise that comes with the model is an essential part of the demonstration. So, what will we do? Well, we will do little touching of the initiation of the depolarization, that is that little thing over there. So what happens is, so if the depolarization is not big enough and you don't reach the threshold, then action potential is not generated. You can repeat this many times. The system will work the same way. However, if the initial depolarization is big enough and reaches a threshold, then the system ladies and gentlemen, please understand, then the system runs in an all or nothing way. It generates a completely understandable and simple result, a full action potential. Now, please understand that the system needs a time in order to regenerate itself. So if you are too close with your second stimulus, if you wait it long enough like I did now, then you can generate an action potential. But if you are too close to the second stimulus, no matter what you do, nothing happens. This, ladies and gentlemen, is called the absolute refractory period. Of course, if you wait long enough, then you can generate an action potential again. If you do in between, then the result will be a somewhat truncated or less appropriate action potential, smaller in size and so on and so forth. So the model is very simple. Anyone can try it at home and work on it and understand how action potentials work. Okay? Everyone understands all or nothing law, absolute and relative refractory periods. Very good. See, the model works. Okay. So, what I also have to say a few words about is action potential velocity. And please note that there are a number of factors that influence how fast action potentials move along the nerve. And the most important are the size of the axon. The bigger, the wider the axon is, the faster the action potential runs. The presence or absence of the myelin sheet. In case the myelin sheet is present, then action potential travels faster. If there's no myelin sheet, action potential travels slower. And temperature. If temperature is higher, then action potentials travel faster. This is the reason why warm-blooded animals are in evolutionary have an evolutionary advantage as compared to what we so-called cold-blooded animals. Actually, these cold-blooded animals Doesn't mean that they are always cold. It means that their body temperature is the same as the outside temperature. And in many cases, they have to sit out in the sun to have their body temperature to be warmed up in order for them to be able to move normally. The difference, yes? Potassium channels cause repolarization. The opening of the potassium channels. And potassium going out. There's so little potassium and sodium go, so little that it does have very, very, very little influence on everything. On the long run, of course, it will eventually deplete the sodium and the potassium difference, and this is why you need the sodium-potassium pump to keep up this difference. But for one action potential, it has very little. Actually, the difference between a cold-blooded, let's say a reptile, and a mammal can be demonstrated by the fact that if you take a snake, please don't try it at home. It's not an experiment that everyone should do. But if you are trained, you take a snake that wants to bite you, and you can catch it. Action potentials in mammals are not that much faster than a snake trying to bite you. Your hand, that is, you're seeing the snake move, your mind sending the information for your hand to move, is so is so fast that you will catch the snake, if you are trained. But please don't try it at home until you practice it. Okay. A few words about toxins that you will encounter, that is things that affect channels. Two toxins are, these are toxins generated by certain animals, succintoxin and tetrodotoxin. Tetrodotoxin is actually 1,200 times more poisonous than cyanide. That is, 1,200 times less is enough to poison a person. A guy working in Japan, he's British but was working in Japan after the Second World War, described these toxins first. And they come from a number of different animals living in the sea that are, or in the jungle. Actually, these are less known than the little fish that lives in the sea close to Japan, called the blowfish or fugu fugu. The fact that these things produce poisons, we know already from the Bible. This is something written in the Bible of what not to eat. And it is taken word by word from one of the translations, of course. The Bible hasn't been written in English, I suppose you know that. All that are in the waters, all that have fins and scales, shall ye eat. And whatsoever hath not fins and scales, ye may not eat. Now, please note that men are have a strange way of thinking. If I tell them that you should not eat this, they don't care, they will try. But if you say that it is unclean, then they won't. So instead of telling them that, look guys, these things are poisonous, so don't eat them, the Bible simply says they are unclean, so don't eat them. So people don't eat them except for certain places in the world where they are considered as a delicious seed. Unfortunately, there are still approximately 100 fatalities every year from people eating these fish. They eat sushi, and sushi is not cooked, so the poison gets into the person, and they die. It happened so often that Japanese wrote small poems about it. For example, last night we ate fugu, today I took his coffin to the cemetery. In such a poisoning, the victim is conscious, fully aware all along as her limbs first are paralyzed, and so on and so forth, until the person cannot move at all, and finally the respiratory muscles stop. And there is very little that one can do. There's another well-known channel blocker, which is still in use, especially if you go to the dentist. It has been used in the old times when rum or something like that wasn't available. If you drink too much rum, you become unconscious. Some say it's much more pleasant a way of getting unconscious than using lidocaine, which is the substance and its relatives. They are called local anesthetics. Please note that local anesthetic doesn't mean that they would not act all over your body. Local anesthetic, the name local anesthetic comes from the fact that they have to be applied in a high concentration. So usually, one application will only act locally because far away from the application, the concentration is too low to act. However, if you apply too much of the local anesthetic, the concentration gets high enough in order to block these sodium channels. Unfortunate examples call our attention to that, where dentists have given too many lidocaine injections to the person and the person died. So, just to reiterate, finally, as a last part of the first lecture, most important properties of the action potential that I would like everyone to know. Well, an action potential is always triggered by a depolarization. The depolarization must exceed a threshold in order to invoke the action potential. An action potential under physiological conditions involves an overshoot of the membrane potential, that is, the usual negative membrane potential turns positive. Action potential is followed by a refractory period. Actually, we can distinguish an absolute and a relative refractory period. Action potential is all or one. Meaning that under the conditions where you evoke the action potential will either go or not. And given the same starting conditions, and I would like to emphasize again, given the same starting conditions, the action potential will always look the same. Of course, if you change somehow the sodium concentration gradient and so on and so forth, the action potential will look a little different. But will always look the same with the same starting condition. And finally, I haven't talked much of this, but I would also like you to know that action potentials, when they propagate without a decrement. That is, if the action potential travels along your nerve, the action potential is the same here, and here, and here. Please recall, I hope that things were mentioned for the electrotonic depolarization. Electrotonic depolarization spread with a decrement. Yes? Was this mentioned? Electrotonic depolarizations 10 spread with a decrement. Wasn't mentioned? Then please note that if it is not an action potential, just an electrotonic depolarization, then this electrotonic depolarization, if you go further and further away, gets smaller and smaller. If you wish, the little here, you can, the little quick is whatever. If you go further, the little quick is, you don't hear it as much. So, finally, the fact that the action potential is an all or none response is due to the fact that the peak of the action potential is not determined by depolarizing stimulus. It is independent whether you just go or you go. The action potential is determined by the sodium equilibrium potential and the time force of sodium activation and inactivation. In other words, if I would use the model, the action potential depends on how much water you have in the tank and how fast can it flow down. That's the only two things that determines how the action potential is shaped. Okay? So the action potential doesn't depend on how strong you stimulate the membrane. It depends on the sodium equilibrium potential. This is how far it will go. And by the time course of sodium channel activation and inactivation, this will set the timing of the action potential. So, if this is just to show you what I have already said, that the things along the axons determine how fast the action potential travels. So if you have a small unmyelinated axon, this is the decrement of the electrotonic potential. Then you have a small, or that is slow action potential travel. If you have a large unmyelinated axon, squid giant axon, then you have an intermediate travel of the speed of the action potential travel. And the best, if you have myelinated axons, we have small and big axons in our body. Most of our axons are myelinated, some touch, and pain fibers are non-myelinated. This will be discussed in detail when you get to neurobiology. This is how this thing looks. I don't know if you have seen this before. This is the neuron with these little cells around, and there you have these so-called nodes of Ranvier. Was this discussed in anatomy? No? Swan cells and no. Okay, so then just look at the picture. It's so nice. What you see actually is the fact that you have potassium channels and sodium channels are in green. So please note that under the myelin sheath there are no potassium channels, and only in these so-called nodes of Ranvier. Ranvier was a guy who described these things between two swan cells. This is where the action potential will be generated. Below the myelin sheath, there is only an electrotonic potential change, and the next action potential will be generated in the next node of runway. So we say that this action potential is jumping from one node of the runway to the next, so we call it saltatoric conduction. You have heard the expression saltatoric conduction before? Okay? So that's the nodes of runway and the action potential traveling along an axon with myelin sheath. Finally, you might come across the so-called compound action potentials in your labs, which is simply the fact that a nerve has many fibers, individual axons, and some are big, some are intermediate, some are small, so the action potential travels along them with different speed. So and if you measure at one point, what will you see? You will see a peak for the fastest, a second peak for less fast, and a third peak for as many for the slowest action potential. And of course, from where these peaks are, one can get an idea how fast these action potentials travel. And actually, fast action potentials can travel 50 meters per second, or even faster. Well, ladies and gentlemen, this concludes my first lecture. We will have, let's say, 5 minutes or so break until I initiate my second lecture.